Welcome to our first flipped classroom video. So we are beginning our unit 1 with a conversation about the scientific method. So you guys have been learning the scientific method and using the scientific method for a long time, probably at least second grade. So this should all be review. But as we go through this year, we're going to be refining and deepening our understanding of the scientific method as we apply it. So it's always good to go back and review. So we're going to start out just by talking about what the scientific method is. So the scientific method is just a logical, stepwise approach that scientists use to find answers to questions. Since it's a stepwise approach, it makes sense to talk about the various steps that we're going to take in the scientific method. It's important to understand that the scientific method is really not linear. It's really a cycle, and it starts and stops and comes back around to the beginning, but we have to start somewhere. So we're going to start out with making observations. Observations are things that scientists make about their environment. So this can be something quantitative, something we can put a number to, something we can measure. This can be length, this can be mass, this can be a number of atoms. It can be quantitative, but it can also be qualitative. What does it look like? What color is it? How does it smell? So observations can be quantitative, meaning attached to a number, or they can be qualitative. And we make qualitative observations with all of our senses. Okay, what does it look like? What does it smell like? How does it sound? We will not taste in the chemistry laboratory. Once scientists have made observations, then they start to state a problem, frequently in the form of a question, because these observations lead us to a question. So if we were to take an example, we might take the example that my aloe plant is withering and drying. So I notice that the surface of the aloe seems wrinkled, the leaves seem to be a little bit yellowed. Those are my observations. So I'm going to state my problem. And my problem here is what's going on with my aloe plant? What's causing the aloe plant to have issues? So that's derived from my observations. Now, once we've made our observation and we've stated our problem, we're going to do some research. This doesn't mean that we're going to Google it. It doesn't mean we're going to go to Wikipedia. It means that we're going to consult research journals. Maybe for something as simple as the aloe plant, we are going to consult the internet. We are going to ask our peers. But more often when we talk about background research, we're talking about periodicals, particularly peer-reviewed journals. We're talking about textbooks. We want to make sure that we are using reputable sources. Once we've done our research, we can start to think of solutions to our problem or answers to our question, and we call that a hypothesis. So a hypothesis is our educated, based on that research, based on that prior knowledge, our educated prediction of what's going to happen in response to a change that we are going to make. And making that change means that we are going to test. We're going to design an experiment. We are going to make a change. We're going to observe the results of that change. Our experiments, for it to be a true scientific method, need to be reproducible. So when we do an experiment, we're always going to have a procedure. And the reason that we have a detailed procedure is so that another scientist or another student can come along and do that experiment and get the same results. If we don't have a clear procedure, that's not going to be possible. As we test, of course, we're going to gather data. That data might be quantitative or it might be qualitative. So if we come back to our example of the aloe plant, when I form my hypothesis is probably going to be that if I water the plant, the aloe plant will recover. And it will stop being withered and it will stop being yellow. So I'm going to design and perform my experiment. Now, this isn't a great experiment because I don't have controls, but I'm going to say I'm going to add 10 milliliters of water to the plant each day and observe what happens over the course of 3 weeks. So you notice that as I design my test, I'm thinking about quantities. I'm thinking about how long. Part of our testing is going to be, what are we going to measure? What data do we need to record? So I'm going to say I'm going to add 10 milliliters of water every day. I'm going to record my results for 3 weeks, and I'm going to be looking at the texture of the leaves as well as the color of the leaves. So now I've gathered my data, and my next step is going to be to analyze that data. And as I analyze that data, I'm going to form a conclusion. Was my hypothesis correct? So did my plant stop being withered? Should my experiment be modified and repeated? So in my case, I might have noticed that while the plant stopped being withered, the leaves were still slightly yellowed. This might mean that I need to make a different change. Maybe I need to add fertilizer to my plant. And so our scientific method is always going to reach a conclusion, and we're frequently going to ask another question. Is there another factor that should be considered? And so we're going to repeat and repeat and repeat. So it's important to recognize that although we talk about it as a logical stepwise method, that it isn't linear. It cycles back around. So you'll notice in our little image here, we have that we're going to start by making an observation. We're going to do some research that's not even in our flowchart. We're going to come up with a hypothesis to explain our observation. Notice that word explain. This is really important, and we're going to come back to that. We're going to test that hypothesis. If our hypothesis fails, we're going to come back up, come up with a new hypothesis, and test again. If our hypothesis passes, if it works, if it does what we expect it to do, we're going to keep testing. Once we've tested it enough times, our hypothesis can become a theory. It has to be tested by many people in many different situations. It has to be published. That research has to be verified, validated by other scientists before it can ever become a theory. Even once it becomes a theory, scientists aren't done. We keep testing that theory. As long as it keeps passing, we're going to continue to use it as a theory. If it fails, we're going to go back up, come up with a new hypothesis, and test again. This is the way that science works. We learn new information. We get new observations. It's going to adjust our hypothesis. It's going to adjust our understanding, and we're going to test again. It's really, really important to recognize that there are two different concepts when we talk about science. There's the idea of a theory, and there's the idea of a law. Okay, many students confuse theories with laws, or they think that if you test a theory enough, it can become a law. A theory can never become a law. Okay, a theory is always going to be a theory because a theory attempts to explain. A law simply states an observation. So as an example, if we were to talk about gravity, the law of gravity says that if you lift an object and you let go of it, it's going to fall. That's the law of gravity. Okay. The theory of gravity says that because the mass of the Earth attracts the mass of the object, when you let go of the object will fall. The theory attempts to explain why. The law just states what. Okay, so a theory can never become a law because a theory attempts to explain a law. Okay, so I hope you've taken good notes. If you have any questions, please make sure to bring them up at the beginning of class. I look forward to seeing you tomorrow.